Lesson 6-6, solving radical equations. So I don't think there's anything extraordinarily new here. I mean, there's radicals, square roots, but you guys know those. And otherwise, it looks like basic algebra 1 rules. I was looking through a bunch of these. I mean, some of these, they do prompt solving with a graph. It's a little different, but I can pull up Desmos and can do that. And then there's a few interesting type word puzzles at the end. I got some word puzzles here. Okay, so, yeah, well, do these. Here, I'll go through the examples. Right, and then do some book puzzles. And so example one, solve square root. Once I do one of these, a lot of these are really just pretty similar in line. Example one, what if you have root of 3x minus 5, okay, and then outside it, so close the root, and then plus 2 after that. And that's all equal to 6. Okay? Now, when it says solving, the implication here is that, well, we're trying to like solve for x, or sometimes a different variable, but it's x. So like, what is x? So we go through a series of steps. It probably looks a lot like algebra 1. And then the last step is x equals something. So the first step is subtract 2 from both sides. So minus 2, minus 2. Okay. It gives me the square root of 3x minus 5. Right. Is now all equal to 4. Ooh, that. Okay. Now, how do you undo a square root? Well, by squaring it. Now, as long as you do that to both sides, boink, boink, everything is balanced. So the square and the root cancel. So 3x minus 5 is equal to now 16. 4 squared is 16. Okay. So now we've unburied the x from the square root. All right, now we're closer. Let's do plus 5 on both sides. Okay. So that's 3x. Sum for x equals, is that 21? Divide both sides by 3. X equals 7. And that should be it. I guess that's the whole thing. Right? It's a lot of the puzzles in this lesson are just like that. Right? And you can always check your answer. I don't know if I made a mistake along the way. Take your answer, 7, plug it back to the original statement, and see if it makes a true statement. Let's try right here. If I plug 7 in here, 7 times 3 is 21. Minus 5, that would be 16. The square root of 16 is 4. So this whole thing is 4. 4 plus 2. Oh, yeah, that's 6. That totally works. Yeah. Let's keep chugging along here. What is example two? Example two. Check out. Got 4 times and then 2x plus 6. Ooh, raised to a 1/3 power. And you guys know that represents a cube root. So there's a different way to write that too, but I do like the fraction exponent myself. Right, minus 9 is all equal to 3. Right? So same thing, we're trying to solve this x, so I'll throw a little box around it. Okay, so that's the goal. Right? And just like the last one, I'll just unbury it one step at a time. Right? So plus 9 on both sides. So plus 9, both sides to balance the expression. So we got 4 times something is equal to 12. Okay? Next step, how about divide out this coefficient of 4? Divide out the 4, divide by 4. Okay? So now 2x plus 6, the cube root of that, or 1/3 power, if you like, is equal to 3. That's 12 before 3. Okay. Okay, now I have to cube both sides to unbury the x out of this cube root. So this is power 3 and this is power 3. Okay. Now on the left side, the 3 into 1/3 fraction, you could think of that as consolidating to 1. Okay. Now on the right side, I got 3 cubed. 3 times 3 is 9 times 3 is 27. So I got 2x plus 6 is now 27. Minus 6. That's 2x is equal to 21. They didn't give us a whole number answer. Huh? All right, that's all right. Divide those sides by 2, 21 over 2. Uh, or what is that, 10.5, I think? 10.5? That could also be valid. Right? Yeah, and we looked at the book too. So they also got 21 over 2. Yeah, so all good, all good. Okay, example 3. Identify extraneous solutions. Because sometimes you get an answer at the end, and then you go back to plug it back to the beginning, and maybe you didn't even make any mistakes along the way, but something doesn't work. Like for example, anytime you have a square root, you have to be careful because you're not allowed to take the square root of a negative to get a real answer. Here, let's see how this plays out. We got square root, example 3. Yeah. Okay, x plus 21, and that's equal to 3 minus the root x, like that. Right? Let's like that. Um, okay, what could I do here? Okay. Now, there might be different ways to go about this. One thing you think, well, you could square both sides to start with. Right? to unbury the x out of the square root. So you could square that side and also square this side. Now, if I square the right side, isn't that the same thing as this expression times itself? Okay. And I'll expand it out that way just so it makes the next step more obvious, which is FOIL. We're about to do some FOIL. I'll spell it out. FOIL. Right, you guys know we're going to deal with that. Okay. Now, I know at the end of this process, I'll still have a square root, so I might have to have some more steps, but we'll see what happens. Now, on the left side, very simply, the square and the root cancel out, so I just have x plus 21. Right. Now, the right side is a little more complicated, though. So 3 and 3 is 9. Then minus 3 root x minus another 3 root x. That's minus 6 root x altogether. Okay. And then root x makes x, but negative negative makes positive. So really, it's just like a plus x right here is what that's going to be. Okay. So now, oh, actually, you know what? Hey, look at this. Look at this. The x and the x can cancel. It's minus x. That goes away. Okay, now I have one. Okay, I was thinking we might have to do something like this again, like square both sides, because normally you have to when you have something like this, but yeah, this little it's a bit easier. Okay, so let's do how about this? What if I add 6 root x to both sides plus 6 root x? Okay. And I'll subtract off the 21 at the same time. Minus 21, minus 21. Okay, there we go. So I'll have 6 root x, solve for x, is equal to, now 9 minus 21. What is that? Negative 12, I think. I think that's right. Divide both sides by 6. So root x is equal to negative 2, square both sides. Oh, make sure that's in parentheses. Okay. So I got x is equal to, and negative 2 being squared would be 4. Okay. Right. Now, careful though, because we do have square roots floating around. We got negatives floating around. Okay. So, I have a suspicion that something might go right here. Let's make sure this actually works. What if I take this 4 and I plug it back into the original statement? So 4 plus 21 could be 25. Okay. And the square root of 25 could be 5. Right. Now, if you terminated plus or minus, maybe the negative version works. Right. But if I just call that 5, let's see what happens. Right. Then over here, 3 minus 3x. Now, 4 was the answer for x, so the square root of 4 could be 2. Okay. So 3 minus 2 is 1. 5 is not equal to 1. Huh. Right. What if I threw a plus or minus on here? I'm just playing around with this in my mind here. So you could go 3 plus 2, right? Okay, then that could be 5, maybe, right? That works, okay? So I'm going to label this right here as being an extraneous solution. Okay? Because if you only consider the positive value of the square root that comes out of this, it doesn't actually work. It doesn't actually create a true statement back at the beginning. Here, I just threw these into Desmos to show you guys the graph version of these. Okay. So my two original statements, I just said y equals to make this equation. So y equals root of x plus 21, that's this right here in red, and y equals 3 minus 3 root x, that's here in blue. Right. And show you guys these two curves. You guys see how these two curves never actually cross? The fact that they do not cross is another way to indicate that there's no solution. It's a graphical way of giving the answer, right? Unless, of course, you did consider this minus being a plus or minus, and same thing with this top one, right? Because then they would cross probably right about here at 5, I think we came across, right? If there was a top half to this blue parabola, sideways parabola, right? It would be, right? But yeah, as it is, yeah, those graphs do not cross. So the supposed solution we got is actually extraneous. It doesn't actually count. Right, example 4. Solve a radical. Let's see, example 4. We got 2/3, and then 11x, I guess we're solving for x, plus 14. Ooh, to the 1/6 power. Ooh, a sixth root. Let's see too many of those. And then plus 8 is equal to 10. All right, so let's just follow regular algebra rules. So first thing is subtract off this 8. So 2/3 times all of this fun stuff is equal to 2. Okay. How about multiplying both sides by 3/2? I think would be the next step. All right, so now this is all equal to 3. So 11x plus 14 to the 1/6 is equal to 3. Okay, 3 right there. Okay. Now I have to take each side to the power of 6 to unbury this x from the radical. Okay. Well, this is going to get pretty big because it's 3 times 3 times 3 times 3 times 3 times 3. What is that? Okay. Oh, actually, that's not too bad. 729. Okay. So 11x plus 14. Okay. So I just cancel out this 1/6 of the sixth power, and I'm left with that. Equals 729. Subtract 14, both sides. So minus 14. Looking at 11x equals 715. I wonder if that's divisible by 11. I hope so. That would be nice. Over 11. Yeah, sure is. X equals 65. There you go. All right. Of course, you could plug that back into the original statement. I'm sure that would work and I'll be good. Oh, yeah, they also got 65. Now I'm looking at same thing. All right. Example 5. Solving a radical equation. Oh, by graphing. Use a graphic calculator to solve it. Okay. Here's what I do is I'm just gonna throw that straight into Desmos and we'll find out. All right, so I just put those into Desmos. Okay. And here's the way I just did that. Here, let me skip this around a little bit. Okay. Is I took this first expression 2 and then cube root of 3x minus 4 plus 10. Right, so that whole thing. I said y equals, and I made that this red equation. So 2, 10, and then 3x minus 4 is in the cube root. I express that as a 1/3 power, right, and then plus 10. And then the other expression, see where it says equals 9? Well, I just said y equals 9, which is just going to be a flat line. Let's take a look, right? Okay, that's the blue line, flat line. It's just y equals 9. That's what a horizontal line could be. Okay. And wherever those two graphs cross, well, that would be the solution. So I can just zoom in here and grab that coordinate, and it gives it to me, right? So x is about 1.29, right? And then some more decimal places, but 1.29. Yeah. So that's the answer. X is 1.29. Yeah. All good. All good. And well, okay. That's what it would be. All right. And last example. We got a word puzzle. Ooh, 1619, a German mathematician, astronomer, Johannes Kepler, published his third law of planetary motion. This is one I cover in my physics class if you want to learn more about that. This states that the square of the time it takes for a planet to orbit the sun, okay, that's so capital T. So for Earth, that could be 365 days or 1 Earth year, right? Uh, that value is okay, the square, or I should say the square of that time is equal to the cube of the planet's mean distance from the sun. Well, okay. I guess in my physics class I would phrase this a little bit differently. I would say that these two are directly proportional for all the planets in the solar system and all the asteroids just within our solar system. So if you take the square of the time and the cube of the distance and you divide those two, it's the same ratio, right? Now your math look like shortcuts this a little, simplifies it a little bit. So when they say equals, it's like, well, okay, maybe but by some factor is true for all the planets and stuff, right? And so Mars, it takes 1.88 Earth years to orbit the sun. Of course, Earth, it takes exactly 1 year to orbit the sun. So I think there's enough information here where you can find out how far away is Mars from the sun in terms of how far away is Earth. Okay? So what they're saying is uh, uh, take the square of the time and the cube of the distance and set those equal. Again, if this was my physics class, I would say also throw in some constant k, but that would end up canceling out. Here, so in physics, it's more like this. So time for Earth to go around the sun, sorry, squared, right, is equal to some constant times. Now, the distance they're calling a, I don't know why they went with a, but I'll just stick with that. So, okay, something like that. And this is for Earth. So Earth and Earth, right? Now for Mars, Mars takes a different time to go around the sun. So it'll be time for Mars. And then that value squared is equal to the exact same constant. So this constant is this constant. It's true throughout our entire solar system. Now, a different solar system is different for different stars. But our solar system is going to say. And then the distance from Mars to the sun cubed right there. Okay? Now, what you could do is, or at least this is how I might approach it, is divide one equation by the other equation. This constant cancels out, which your book never mentioned. So that's where it goes away anyway. Okay? And then I think we know three of these four values because you can say the distance from the Earth to the sun, we'll define that as one astronomical unit. They time for Earth to go around sun would be exactly 1 Earth year. And they also told you the time for Mars to go around is 1.88 Earth years. There's enough information lying around where you can solve for the distance from Mars to the sun. Okay, okay, so yeah, they set it up a little bit differently, but I'm just going to finish solving up. the way I have it set up here. So I'll say 1 year, then square that, divided by 1.88 years, then square that, is equal to, I'll call this 1 AU, called an astronomical unit. That's the distance from Earth to the Sun is defined, right? So that's cube, right? Divided by the distance from Mars to the Sun, so A, also being cubed, right? And see, this is what we're solving for, distance from Earth to, there's a Mars to the Sun, I should say. Yeah. Okay. And we're going to get it in terms of astronomical units, because years can't, well, year squared over year squared, whatever that equals. Right, so now what? Well, hey, maybe I could cross multiply. Right, there's a cross multiplication. So I can take this and cross multiply up here, and this cross multiply up here. All right, I'll spell it out. Cross multiply. You're allowed to cross multiply across an equal sign or multiply both sides by that denominator value, however you think of it. So the distance from Mars to the Sun cubed is equal to 1 AU cubed. Well, so basically, uh, I'll just drop the unit, call it 1 cubed. Because by the time I take the cube root, it'll come out to astronomical units anyway. And then times 1.88 being squared, which came from here, cross multiply, looks like that. So the distance from Mars to the Sun is equal to whatever 1.88 squared, and then the cube root of that is. And I can express that as a power to the 2/3. Right? So distance from Mars to the Sun is, okay, calculator time, what's 1.88 to the power of, and then parentheses, 2/3. I'm getting 1.52, and then string of numbers, so I'll just cut it off there. Okay? And this would be astronomical units, also called AU. If you ever see that, if you take an astronomy class, in 1 AU, of course, is the distance from Earth to the Sun. If we do that. So yeah, so I think that would be the answer there. See what they get. Okay, yeah, they got the same thing. Same thing. All right, so there you go. All right, jump into the book questions. And so I got a few of these highlighted. Yeah, solve each equation. So number 5 says square root of k we're solving for minus 4, and then outside the root got -1. This is all equal to 5. Right, so first thing you think is, hey, let's do +1 on both sides. So I'll get square root of k we're solving for minus 4 is equal to 6. Okay. How about square both sides to get rid of this radical? Square. Okay. So now k minus 4 is equal to 36. And do +4 plus 4 k equal to 40. Okay. That should be it. All right, here. We're getting pretty good pace, so I'll plug this back and see how it works. So what's 40 minus 4? That would be 36. The square root of 36, I'll call 6. 6 minus 1. Yeah, that's 5. That totally works. All right, we're good. We're good. All right, number 11. So again, solve each equation. This one's a cube root. Oh, 11. All right, so I got the cube root of 2v minus 7, right, and that's all equal to -2. Okay? Right, so I'm solving for this v. What does that be? Okay. Now, the cube root is more straightforward because now I will keep both sides, but the fact this is equal to, a negative value means it'll still be a negative value. You have to be careful with even roots, like square roots, because or you're not allowed to take the square root of a negative value that can give you extraneous solutions and no solutions and so on, right? But cube roots, usually you don't have to worry about that so much. So 2v, or any odd power, is usually safer. 2v minus 7 equals, now 2 is 8, the negative, so negative. Next step, +7 plus 7, 2v equals -1, and divide by sides by 2. V equals -1/2. Okay. Does that really work back in the beginning? Let's see. 2 times -1/2 would be -1. -7 is -8. And the cube root of -8 is -2. Yeah, it really works. All good. 13. Solve each equation. Ooh, identify any extraneous solution. So to give you a hint that some of these you might get a solution, but it doesn't actually answer the original question. Let's find out. Right. So square root x minus 15 equals 3 minus the root x. Interesting. So my first thought is probably square both sides and see where this leads. But we're not going to get rid of the roots because of foiling, FOIL. In fact, here's something I did back in the example. So is instead of doing square, I just rewrote it next to itself, multiply, because that's the same thing. Also squared, isn't it? Just to set up the first, outside, inside, last FOIL. Okay. That's a stratus. So on the left side, the square and the root cancel. I just have x minus 15. On the right side, well, got this whole FOIL process. 3 and 3 is 9. Minus 3 root x minus another 3 root x. That's minus 6 root x. And then minus root x minus root x. So that'd be the minus minus becomes a plus because it multiplies. And x. So like that. This looks really familiar. Is this the same example we did earlier? I mean, this just feels so familiar. Well, I don't know. Actually, it's not too far off, isn't it? I'm looking at it. Yeah, that's all right. Okay. Yeah. Because next thing that happens is those x's cancel, right, or you could subtract x from both sides. Maybe I should say it that way, right? And then okay, let's do minus sign on both sides. Minus sign, minus sign. So this gives me, is that negative 24 equals negative 6 root x, right? Now, I should cancel off the negatives. Let's divide both sides by 6, right? And then I get the root x is equal to 24 over 6 is 4. And then square both sides. So square, square should be 16. X equals 16. Okay. Now I'm getting x equals 16. But let me check and make sure that works. So they don't have one of these extraneous solutions. Let's just make sure it works. 16. So back to the original statement. 16 minus 15, that'd be 1. Right? The square root of 1 is 1. Right. How about over here? If I plug in 16, I get square root of 16 would be 4. 3 minus 4, oh, that's negative 1. That's negative a positive 1. Right? Again, this only works if you consider the plus or minus solution on the left side, which you're probably not supposed to do. So I think this actually would be an extraneous solution, probably what they're looking for. Yeah, and just like before, if I threw these graphs into Desmos, if I said y equals this and y equals this, okay, then the curves would never cross unless you consider the plus minus version of this to make it a relation, but that would no longer be a function. So they're probably looking for an extraneous solution right here. All right, 21. Oh, use graphing calculator. So it's about to be Desmos time. Yeah, so I'll just do that. I'll just pull up Desmos and pop that straight in and see what happens. All right, let's see. I just plugged those in. Right, so I'm looking down at the bottom of the page. It says root of x minus 7, and then outside the root is plus 2, and the whole thing is equal to 8. So I made each of those an equation. I said y equals. So y equals root of x minus 7, and then outside the root plus 2. And then the separate equation, y equals 8. So wherever these two cross should be the solution. And I haven't seen it yet, but I'm scrolling out so I can't. Yeah, it looks like they cross right here, where x is 43. Hey, that's a whole number, 43. Okay, 43. Right. So if the answer is 43, then I should be able to plug that in. I'll do that. Right. I think we're making really good time on this lesson. So I'm going to try that out. Square root of, instead of x minus 7, I'll say 43 minus 7. Let's just see if this actually works. And then plus 2. Right, that's equal to 8. Right. Now the 43 I got from Desmos, which they prompted doing anyway. So it's solved with graphing. I'm just checking my solution. 43 minus 7, I think that's 36. Right? So I square root 36, then plus 2 equals 8. Okay. Really, this is a question. We're trying to test the statement. Root 36, like 6 plus 2. Is that equal to 8? Oh, yeah, 8 is equal to 8. Bing! Yeah, we're definitely good. Oh, yeah. Oh, yeah. 26. Twine. The largest ball of twine started in 1953 by Frank Stober. After 4 years, the ball had a volume of approximately 268 cubic feet. What was the radius of the ball of twine at that time? Around the answer to, oh, nearest 10. Okay, good. So it's going to be a funny answer, but we can use a calculator to get some decimal approximation. Give you guys a picture here. And so we got this big old ball of twine, it's all twining around, and it's so huge that it gives this volume. Look for the radius. Well, it's probably a sphere. I think we're talking about a sphere here. So I do need to know the volume of a sphere. Do you guys remember that's 4/3, and then pi radius cubed could be the volume of a sphere? Okay. So the radius could be this right here, right, that we're solving for. Yeah, that's the question. What's the radius? So they told us the volume right here. They gave that I use 268. That's cubic feet. So the radius will be in feet. Okay. It's equal to 4/3 pi, and that radius we're solving for cubed. Like that. So, okay, well, I can multiply both sides by 3/4, divide by pi. Here, say that as my next step. So the radius we're solving for cubed is 3/4, and then also divide by pi down here, and then times 268. Okay? So the radius would be the cube root of all this. So it's 3 times 268 over 4 pi. Right, and that whole thing is raised to a 1/3 power, as in a cube root. I'll say approximately equals because I'm gonna cut it off at what is it, the nearest tenth of a foot. So you can sort of think that like approximately the nearest inch, right? Because there's 12 inches in a foot, it's kind of close to 10. So what's 3 times 268 divided by, and then in parentheses, I have to have the 4 pi down here. All right, so it's really important that you group this correctly if you want the correct calculator answer. And that's all raised to the, and then in parentheses, 1/3 power to make a cube root. I'm getting a, oh, well, look at that. Interesting. 3.99957. That would be 4, wouldn't it? Okay, so 4.0, and the unit that stuck around is feet. Yeah, 4 feet. 4 feet. Okay. So here, check my answer. Supposedly, if you have a big old ball with a radius of 4 feet, it should have a volume that's extremely close to 268 cubic feet. Right, let's see. So it's the 4/3 times this pi times 4 feet to the power of 3. Let's see if I get something pretty close to 268. 268. Oh, yeah. Oh, yeah. That is it. Geometry. Geometry. Let's see. Yeah. The lateral area of a cone with radius r and height h, so it gives a little picture. That's nice. Is given by this expression. Here, I'll write that out. 43 as, okay, so lateral area, they're calling L. That's equal to, okay, we've got a pi in here, we got the radius, and we got a big old square root of radius squared plus height squared. This little bit right here sure looks kind of Pythagorean. I'm sure that was part of a larger process. Maybe that could be the length of this diagonal, couldn't it? Yeah. Um, a cone has a lateral area of 65 pi square units. Okay, so they just told us this value right here is 65 pi. Okay. And a base radius of 5 units. So they just told us this radius right here is 5. Okay. I guess that would also go here too, wouldn't it? Times the square root of 5 squared plus h squared, right? Now, I guess the question would be, what is the height, right? Is that what they're asking? Yeah, that's exactly the question. What's the height of the cone? Because that's the last thing to solve for. Legit. All right. Well, one thing I see right away is I could divide both sides by 5 pi. Yeah, that'd be a good first step. So that cancels. Okay. I think it's 13, isn't it? 65 and 5. Yeah, 13. Okay. Here, I'll swap both sides while I'm at it. So root of 5 squared plus h squared equals 13. So I've got that. Okay. Square both sides. So square, square. Right here, the square and the root cancel. Here, while I'm at it, I'll say 5 squared is 25. Okay, so I got 25 plus h squared equals 169. Then subtract 25. So 13 squared minus 25. Getting h squared equals 144. Oh, well, I know what the square root of that is. It's last step, square root. 12. Is this what, inches? Is that, well, it's units. They just say units. So whatever the unit is, 12 distance units. There you go. That's it. Boom, boom. Okay. And one more I got for you guys. 44 tethers. I'll get another picture. The tether length Y secures a telephone pole at 25 feet off the ground. Okay, so the telephone pole itself is 25 feet tall, and there's this diagonal tether. The distance from the tether to the pole along the ground is represented by x, that's this horizontal distance right here. And Pythagorean theorem, x squared plus 25 squared would be this y squared. Okay, here. So then, what if, right, here's our last interesting condition. What if this x plus this y was 50 feet, right? Then what's the value of x? Right, so let's get this picture bigger for you guys. Is right, so it looks something like this. Right, here's the telephone pole. Right, here's the diagonal part of the tether. But there's also this base length. Okay? So I know that this side right here is 25 feet. I know that. Okay. This diagonal we're calling y, and this base part we're calling x. So I know that y squared equals x squared plus 25 squared. Well, 25 feet, but I'll just call it 25. Okay. That's the Pythagorean theorem. Now they did give it to us with one more step. They said y equals the square root of all that. Okay, so I'll jot that down to you. 25 squared, by the way, is 625, so let's do that one. And then there's one more condition they gave us. They said, what if x plus y, so maybe like the tether's like bent down here at this corner and goes back, is 50 feet. That was called 50. Okay? Then what's the value of x? Okay, so that's the question of the value of x. Okay? So what can I do? Now, I sort of have a system of equations here. Mark that as system. Okay. Uh, there might be a few different ways to do this. One thing I see right away is if y is equal to this expression in terms of x, can I just substitute that in for this y right down here? Totally do that. Let's see what happens. See where this leads. So x plus square root x squared plus 625. It's in my radical bar a little bit right here. It's all equal to 50. Okay. Let me do this. I'm going to subtract this x over, and then, okay, it's going to look like this. Square root of x we're solving for squared plus 625, right, is equal to 50 minus x. Okay. Now, if I square both sides, that would be balanced, right? And that would also get rid of the square root. So on the left side, I'm closer to unburying that x. Right? That's why I would be doing that. Right? And the right side, I'm gonna have to FOIL this, FOIL. Right? So left side looks like x we're solving for squared plus 625 equals on the right side. First, outside, inside, last. So 50/50 is 2500. Now, the outside inside is going to be minus 50x minus another 50x. So it's going to be negative 100x. And then negative x gives you plus x squared. So we've got, and we're solving for this x. So that we can, yeah, that was that the direct question? Yeah, what's the value of x? Oh, look at this. Minus x squared minus x squared. Ooh, okay. I was thinking halfway through we are going to have to run into the quadratic equation at some point. But no, x squareds go away. So see, I could subtract over 2500. That's 2500 right there. So what is 625 minus 2500? Right. So I got negative 100x equals negative 1875. Then divide both sides by negative 100. The negatives cancel. And then I think x would be 18.75, right? And then the unit was always feet, so I'll just kind of restore that. Right? That should be the answer, right? Now, kind of curious to go back and check the original statement and just guarantee that works. Like if x and y adds up to 50, well, if I took 50 and I subtracted out the x of 18.75 we just found, that would tell me that y equals 31.25. That would be feet also. I'll put that on a little thought cloud. They didn't ask for that, but they could have. Right? And if that's true, then does this x squared plus 25 squared really create this y squared? I can check this Pythagorean theorem from that was like the first line that I wrote. Let's test that. So let's go 18.75 squared plus 31.25 squared, and then take the square root. No, sorry, go back. Okay, sorry. 18.75 squared plus 25 squared. That's what I meant to do. Okay, boom, boom. Okay. Then take the square root of that. Yeah, 31.25. It worked exactly. That's a wrap on 6.6. That's a wrap on Module 6 and first semester.